Hello and welcome everybody to Advent of Code 2022, day 20, being recorded on day 22. So we're still a little bit behind, but I think I might be catching up at a little bit of a better pace now. Day 20 was relatively straightforward. It's kind of a nice problem. I wasted some time on it. I think I had an initial assumption about how I could approach this that I so I implemented that. It didn't really work, and then I started questioning whether that was the right thing to do, and it turned out it was actually a nuance in the input that I completely overlooked that was throwing me off. So then when I figured that out, I went back to my original solution, and it actually did work. And then the solution for part 2, more or less exactly the same as for part 1. No real change in what the code was actually doing. So I think I have a pretty efficient solution. There's one bit in it that I think you could optimize to speed it up a little bit, but it's not super slow, so I'm pretty happy with it as it is. So with that said, let's dive in to day 20, the Grove positioning system. So you're about to go back and meet up with the elves again, but you need to know the coordinates of where this Starfruit Grove is. So you found the coordinates on your device, but it turns out that they're encrypted. So you have to take a stab at decrypting it. Now, they give you a method of decrypting the data that you have. So essentially what our task is to run that decrypting operation on the data we have and get some numbers out of it at the end, which will be our answer. So they give you their file, the input file, which looks like this. We're told that this is, so they give it one number per line, but we're told that this is actually just it's a sequence of numbers like in an array, but that they loop back around on themselves. So if you were to start, so it's basically like a ring buffer type thing. So if you were to start at one index, you count up, and then when you fall off the end, you actually end up back at the start. Now, the reason why that's important is because it says that the decrypting operation is this thing they call mixing. And what the mixing does is for any given number in your list, so they give the example here, you start with that number, and to mix it, you move it the number of positions left or right based on what the number itself is. So in this case, we've got the number 1 as the example. So to mix this, you need to jump this number 1 index to the right. So you then basically hop over the number 7, move it up so that it sits now between 7 and 8. And then if it's a negative number, you do the same thing. Except in this example here, they also show you what should happen if you fall off the end, basically. So you hop over, so -2, you're going to go 2 to the left. So you hop over 4, and then you want to hop over another one. But effectively what you're doing is you're hopping over the last index here, which is 9. So your -2 ends up in the second to last position here. Okay, so you're basically doing this kind of shifting operation around. And what you notice in the example that they give, they've got like, oh yeah, sorry, you're also told that you have to do this for every character in order. So if this is your original array, you have to take the character index 1 and you have to move it so that it forms something. Then in that new array that's formed, you have to identify where character 2 is, and you have to do its mixing operation. So it doesn't matter how you've mixed these, what ends up, you have to maintain the original order. So basically you want to keep a copy of the original order so that you can find which characters you are to mix, so on and so forth. This scuppered me is, and because they don't give it in the example, in the actual input, the numbers are non-unique. So this input is only 7 numbers and they're all unique. So you just go through one by one, find each one, and then just do the mixing operation. In your actual input, there's about 5,000 records, and for me there was about 3,500. There was only 3,500 unique values. So my original algorithm was broken because of that. I made an assumption that there'd only be uniques, and there wasn't, so that broke mine. But my actual assumption for how to approach the problem did actually work. So let's have a look at how I did it. First thing, we start creating our initial array. So just read each line and read in the value into an array. The value that I'm actually putting in here is basically, it's a sort of a hash, or it's sort of a hashed value, yeah, where I take the actual value and I stick it alongside an index, which is the original index for that value. And that is the key part that you need for when you have duplicate numbers. So if you don't have duplicate numbers, that becomes irrelevant. But if you do have duplicate numbers, it's important, because you need to be able to know that, well, it's not that -2, it's this -2. And you can tell that by the index for the original indexes and stuff. So I make this data set, then I take a copy of that data set so that I have one array that I can modify and one array that stays static. And what we do then is we want to take the static array and we loop over every value in it. This check here is a simple check. This is for a case up here where you have a 0. So zeros don't move around in it. So I didn't encode anything into the 0. I just left it as the integer value 0. So this array has the integer value 0 and then a bunch of strings that are an encoded version of the actual value and the original index of it. So the 0 is just, it's a do nothing case, so we can skip the 0. So to get the value out, I do just a simple splitting operation. And then this part here is the important part for where you want to find what index that number is. So you can use this find index method for an array. In Ruby, what this will do is it will return the index the first time it finds the value in the array. So if you have two, say, number 2s in the array, you start it to start and you'll be moving along. As soon as you hit the first one, it'll return that index. But if I actually wanted the second one, then this will give me the wrong result. Hence why I have this hashed version where I'm like, well, it's the number 2 and index 0 or index 1 or 3 or whatever it is. So then when I do this find method, I can find the actual one that I want, and then I can extract the value. I extract the value out of it by doing this splitting operation on that string. So it's a little bit abstract, but that's what we do. Now, this find index method as well, this is probably the biggest part of optimization we could do here, is that this is pretty slow because it's basically an order n operation. So as the array gets bigger and bigger, you have to search through more and more characters to find any given index. So if it's near the start of the array, it'll return relatively quickly, but if it's not, then it's pretty slow. So you have to search through mostly all of the values to get the one that you actually want, which isn't great. You could probably do this more cleverly by maintaining, some sort of hash or something of the different indexes and what the values are, but I wasn't going down that route. This does complete quickly enough that it's not a huge problem for either part. So yeah, I just left it as it is. So anyway, this is now the critical part for this question, is how you move the value, how you decide how you move the values around. The way you want to do this is for the initial case we saw, the numbers were all quite small and all the numbers happen to be less than the length of the actual array itself. But for the real inputs for this, the numbers are quite large. So you've got, like, if it's the length of the array is like 5,000, you've got index modifiers, so values that are in the range of like 8,000 and stuff like that, which means that you would overflow either end of the array. And we're told that, well, in that case, it circles around, so it's a loop. Now, a way you can do that is by using some mod arithmetic on the actual values themselves. So if you think about it, if your array, so the mod operation will always return you a value between 0 and whatever you're modding by. So if you mod by the length of the array -1, that's important because we're using the way indexes work. If you mod by that number, it'll always give you a number between 0 and 4999 in this case. So even if it says, okay, we're at this point here and we want to move 8,000 spaces, we don't actually want to move 8,000 spaces in our array. All we actually want to do is take 8,000 mod 4999 and that'll tell us, oh, we actually want to move 3001 spaces in the direction, and that's what we want to do. So that's our new index that we want to get to. And that will work for any arbitrarily large number. So it basically takes out the number of full cycles that you've done, because that's irrelevant. It just brings you back to the same point, and then just gives you the remainder number of cycles, because that's all that's actually going to matter in shifting you from your current location to a new location. Effectively, then what we do is we delete the value out of the array where we are, and then we insert that value into its new position in where we found out. That seems simple. There's just one crux that I found, and I don't fully understand why this is happening. But basically, if your move to calculation ends up being 0, you have to add an extra minus number. So this is, you've done your calculations, and it's telling you to insert into the 0th position. But in that case, what you actually want to do is you actually want to jump over the last one, so or the first entry. So that ends up cycling back around, and you end up needing to push one out on the far side. So yeah, that's a little bit of it was a weird one. I found it in the sample, and yeah, that's just what you have to do. It works fine on the other side, because if you end up with the 4999 and you do the mod, it actually tells you to go to 0, so that works out fine. But yeah, anyway, that's just is what it is. So yeah, you delete from the old location, you insert into the new location, and that's basically it. We're told then to get the value for our answer. You want the 1000, 2000, and 3000 numbers after the 0 that you have. So there's only 1 0 in the array, that's for sure. So you can do another mod operation. You take the 0 index, you add 1000, mod with the data size, and that gives you your numbers. So you take the 3 numbers, add them together, and hey presto, there's your answer. So if I run that, runs in, I think, it's just under 2 seconds for the first part. And yeah, I'm pretty happy with that. It's not too complicated. It's not a lot of code anyway. Works pretty well. I would like to speed it up by figuring out a better way to do this, because I think this is probably where it's most slow. The rest of the stuff in here, the modular arithmetic, is quite fast, and obviously this is just it looping over an array, so it's an order n operation again, which is pretty quick. So that's part 1. Part 2, let's see how they change it. So they say for part 2, so yeah, you got your answer for part 1. The coordinates, once you've decrypted it, they're wrong, and then you realize that you actually didn't do the full decryption process. So the full decryption process, you have to take each number and multiply it by this decryption key, which is just a set number they've given. And then you also have to run the mixing operation 10 times, one after the other. And they also state that each time you run the mixing operation, it starts back to the original list again. So you go through the original list once, and then whatever that state of the array is, come to the next time, but you go back to the original list for the order again, and you do it again, and you just do it 10 times. So the code is more or less exactly the same. They even tell you the way you get the answer at the end is the same. You're going to have different numbers doing it. So I'll have a look at the code for part 2. And it's very, very similar. The only thing we do is at the start, when we're reading in the numbers, we multiply our number by that big decryption key number. And then the main body of our loop that we do for the data set, we just do it 10 times. That's it. And that works. That's it. Simple as. Gives you the right answer. So if I run that, it's also not too much slower. It runs in a handful of seconds. Yeah, so that ran just a little bit over, just a little bit more than a second longer to run that than to run the first one. And there you go. There's your answer. So yeah, that was a nice kind of fun problem. I wasted time getting myself confused, but if I just stuck with my initial instinct and looked at the input data properly, non-unique inputs are something that you should really, really just look at. Like if you're making an assumption about the state of some of the inputs, you need to validate that assumption. because you can't be certain. And I did that. I made the assumption they'd all be unique, and they weren't, and that absolutely absolutely screwed me for ages. So I got really confused, and then I started questioning myself and pulling my hair out, wondering why my modulus maths wasn't working, and then I was questioning whether that was even the right approach. Anyway, we got there. And yeah, it's not too complicated. So that was a nice fun one. I'm going to have a look at day 21 now. It's still relatively early in the day, so I'm hoping that I can make a good stab at day 21 this evening maybe, and then I might call myself back to just one day behind as opposed to being 2 days behind. Anyway, I hope you had fun. I hope you enjoyed that, and I will see you guys maybe later on. Fingers crossed. Bye bye.